Hello everybody and welcome to Senergy Petroleum's educational training series on GF-6. Today we'll be taking questions throughout the training, so feel free to ask any questions on our YouTube chat. It's going to be right here on the right-hand side of your screen. If you guys do have any future questions, feel free to comment below on this video once it has been posted live. Russ and I will go back in there, see if you have any future questions, maybe you just don't have anything on the spot, and we'll answer those in the future for you. Now to kick off the training, this man has a degree in chemical engineering, 2 STLE certifications with over 25 years of industry experience. Let me introduce you guys to your host, Russ Seidemann.
Thank you, Andre. Good morning. Welcome back to our training series. Done a little bit differently this time. Those of you who have participated before have been here in the training room in Gilbert. So thank you for joining us. And before getting started off here, we're going to make sure that we are safe. I brought with me my Fluke 62 Max infrared temperature gun with 10-to-1 spot ratio and IP54 dust prevention. Let's get a reading here. All right, we are good. All right, again, welcome. And we're here today to talk about the new service classification for passenger car engine oils, commonly known as GF-6. That's the ILSAC designation, also API-SP. This classification, brand spanking new, just became effective May 1st. So this is all really new stuff and timely stuff for you. And let me go over the areas we're going to cover and how we're going to cover them for you this morning. We got this carved up, as I usually do, into 3 chunks. The first section, we're going to just kind of give a review of passenger car motor oils and what you need to know, what you need to take away. For anybody that's the first time joining us, this is a good review of a few basics. So we're going to cover both the product background itself as well as the classification systems and how they work, what their history has been. Okay, so once we're done with that, we're going to talk about the engines and what's driving this change and these changes for GF-6, the engine design changes that are new. We'll talk about the new technologies involved and then what the oil is being asked to do to compensate or to assist in the new engine technologies. And then the third area we're going to cover are kind of the specifics of GF-6 itself, the different features of it. We're going to go over what the new engine tests are having you do, and then what the new product specifications actually are. All right, and we're going to do this. If practice is any indication, it's going to take less time than our regular ones do, than our regular classes do. All right, if you've been in any one of our on-site classes or much of my other presentations I've done, I usually start off talking about a formula. This is the 101 of lubricants. All lubricants made to this same basic formula. In this case, our motor oil. Motor oil is made up of base oil plus additives. Base oil plus additives. And base oil is the wet and slippery stuff. It is just an oily oil. Different viscosities, and we could spend another class learning how to do all that stuff. But that's the basics of it. The base oil can either be a mineral oil, all right, the stuff out of the ground and gone through the refinery. Could be a synthetic oil, a man-made kind of thing with some superior characteristics. Or it could be a blend. And you actually are seeing quite a trend towards synthetic blends and full synthetics because it's very difficult to meet the demanding requirements of newer oils with just a straight mineral oil. Very, very difficult. So you are seeing that trend in terms of base oils. But base oil is not where the GF-6 action is, if you're so inclined to call it action. There's a lot more going on the additive side of things. And motor oil, as a rule, motor oil is probably the most additized lubricant product that we sell. You can have up to 35%, 40% maybe even of motor oil can be, not always is, but it can be additives. Additives are added usually to compensate for something that the oil is lacking or to improve some other performance. And lots of additive changes needed to be made for GF-6 to get our oil to behave better in the engines. There's maybe almost a dozen additives here listed. Most of these probably have some modification as part of GF-6. And you can see that they benefit things like the oxidation resistance, the viscometrics, how it behaves as the oil gets colder or hotter, as well as things like how much sludge ends up in there. Okay, this is all additive-based stuff. All right, so base oil, additives, that's the basics of that. The next basic we're going to look at is viscosity. Okay? Viscosity is resistance to flow. This is resistance to flow idea is pretty intuitive to most of us, right? You pour some water out, you pour some honey out, you get an idea. One is a higher viscosity, one is a lower viscosity. We all have that idea. And it's important to note that viscosity varies with temperature. Now, how much it varies with temperature is another question. You know, the stuff does thin when heated, and everybody who's ever warmed up maple syrup can see that happen. It happens with syrup. I mean, it happens with motor oil. It actually happens with water. You need to you have the right equipment to measure it very carefully, but as you heat water up, it also thins. All right, well, let's leave water and go back to our motor oil, if you will, and take a look at this. This device here is a way we measure viscosity. This is a bath viscometer, a J-tube bath viscometer. Viscosity is measured in these devices, and you can see that area that on there is a heated bath. We maintain a constant temperature because, like we said, viscosity varies with temperature. Inside this bath are these J-tubes or U-tubes that the oil is run through. And here's an animation example of how it goes through there. And see, we've got a stopwatch as part of this process. So let me go ahead and run this for you. All right, this J-tube gets filled up with oil, and we let it run, and we start the stopwatch now, and we stop it at point B. So we've timed how long it's taken this oil to flow through this known segment. All right, and we take that oil and we take that timing, that number of seconds, and we take a certain calibration code from the J-tube and we plug it into another formula, and we end up with a number that is the viscosity. And the typical unit of viscosity measurement, and there are a whole bunch of scales, but most of them are pegged back to this unit called the centistoke. Centistoke viscosity then is also always reported at whatever temperature our oil bath was at, okay? All right. Now in the case of engine oils, we do this testing at 100 degrees C, which is about 210, 211 F in that temperature. And we do it at that temperature because that's a typical temperature that an engine is going to be, or an engine oil is going to be seeing in service when it's operating. Okay, so it gives us some realistic view. So we've heated it up there. We went to our chart, we got the number, we found out what our viscosity was in centistokes. Okay? Now there are two other important viscosity measurements we do on engine oils, because if you ever tried to start your car on a cold morning in North Dakota, you realize that it's not 100 degrees C. Okay? So we do some cold temperature testing. And cold temperature testing is done with a little more elaborate machinery. I mean, one of them is working on a little cold cranking. I mean, but basically both of these are run at very cold temperatures. And we're measuring how much torque it takes to spin it up, and does it really flow. So we run these cold temps. We take this other temp that we ran at 100 degrees C, and we convert it to an SAE grade. Okay, so now how do we do that? Well, the SAE is the Society of Automotive Engineers, and going way, way, way back, they developed a viscosity grading system called the J300. And the J300 chart is this chart right here. All right, so the J300, we take our viscosity information from the cold tests and from the warm test. and we go to the J300 chart. So let's take a close look at that chart. And you can see the chart has along the left is the actual SAE viscosity designations. The next two columns in from the left are the results of your cold weather, cold temperature tests, what kind of numbers you came up with. And then the next two after that are some of the higher temperature numbers. So if your cold temp tests showed you to have a 5W, and your test at 100 C showed you to have a 30, your resulting engine oil grade is a 5W30. All right? It is just that straightforward. Run the tests, you go to the SAE chart, you get your viscosity grade. Okay, so that's pretty clear how that's done. And those tests from time to time are slightly modified, but they've been around and established for quite a while. What you might need to know for your useful information, because we're all familiar with certainly most of the common grades in use, is what the upcoming trends are. And there has been a trend both in heavy-duty engine oils as well as passenger cars on lighter viscosities. The reason, and it should be pretty straightforward, which is it easier to swim through? A swimming pool of honey or a swimming pool of water, right? It's easier to swim through the thinner stuff. You got to do a lot more work to get through the thicker stuff. Which one is going to give you better economy in an engine? The engine that's fighting thick stuff or doesn't have to fight the thin stuff? And that's exactly how it works. The thinner oils give better fuel economy, assuming you've designed your engine well enough to tolerate thin oils and you're not sacrificing any wear. What is remarkable is that is the case. The engine designers and builders are doing some remarkable things with some very, very thin oils. And that leads us to the current trend, the newer viscosity grades. Of course, driven by fuel economy and emissions, we're talking about 0W16. 0W16 is actually in the US market right now. Coming along, 0W12 and 0W8. These, I believe, are in Japan currently. Honda developing with these. 0W8 is remarkably thin stuff. It is just marginally thicker than diesel fuel number 4. Typical diesel fuel used, for instance, in an ocean liner. Just amazing what they're doing with it. All right. Okay, there's our that is our discussion of the basics of viscosity and viscosity measurement. Let's take a closer look now at the other important aspect of engine oil in basics, and that is the quality of the oil. Because you could submit a jar of honey for an SAE grade and end up with maybe a 10W30 honey. Would you put that actually in your car? I hope not. But you would put an oil in, and an oil that is the right quality. So we're going to talk about the quality levels a bit, okay? And I'll take you through a little bit of this discussion. Okay, engine oil quality is determined in the world generally by 3 organizations. They're the most actively involved. The American Petroleum Institute, which is involved in the North American market and is largely populated with by oil companies. The ILSAC, the International Lubricants Specifications and Approvals Committee. The ILSAC is in the North American market, and it's made of engine OEMs. The North American OEMs and the Japanese OEMs are part of that group. And then the ACEA. And the ACEA is the European engine manufacturers. Now, for our purposes today, and what we're talking about, which is the ILSAC GF-6 and API SN, we're just going to talk about those guys, right? The ACEA has their own specifications, and they're not part of this new change in the market here. Okay, here's some history timeline on engine oil quality as based on these service classifications. Okay, we're currently at or have been up until May 1, we're at API service level SN plus. The new one is API service level SP. Okay? If you count your way backwards, these are all done alphabetically, so that the oil for old engines way back in the day was just a straight mineral oil, no additives. That's API SA. You put in just a touch of maybe some antioxidation additives, you're probably at API SB. And over time, all of these things have progressed. Engine oils have gotten better through SC and SD and SE and SF, all the way up to now where we're at SP. And you can see that, of course, along the timeline. It's designated where the years are. And you can also see that it was about 1992 when the ILSAC got involved. All right? I'll talk about that in the history slide here next. And the ILSAC came in and started joining in. They started with their specification GF-1, and that's been growing to GF-2, GF-3, and on to now GF-6. So here's the history of how the whole thing was structured. For a long time, for decades, there was a group called the tripartite group of the API, the SAE, and the ASTM all got together in these committee meetings and group meetings, and they kind of mashed together and figured out what the engine oil performance standards should be. Well, in 1992, the ILSAC was formed by the OEMs of the engines themselves for North American sales, who decided that the API and this whole tripartite system wasn't working fast enough, that it was not keeping up with the engine technologies that they were building off into the future. So they wanted a bigger say, and they generated their own group to do it and their own specifications, again starting with GF-1, okay, GF for gasoline fired. So they've got their own structure starting in then. In general, we've got a match between the two of them as they go along. These two groups work cooperatively in developing these tests and these specifications so that there always has been a correspondence between the GF classification and the API service classification. Okay, and that's why both GF-6 and API SP are coming on at the same time. So two groups, are there any differences, you might be asking? Well, the biggest difference, the most noticeable difference you'll see between the two, viscosity grades. Okay, the viscosity grades. The ILSAC does not permit straight grades or any viscosity grade over an SAE 30. Okay? Remember, these are the OEMs. They're focused on passenger car, and and part of the key of their focus, of course, has been fuel economy. So for them to have multi-grades that are lower viscosity, definitely in their purview. The API has a broader scope of who they're serving, and they do include the straight grades, a 30, a 40, 15W40, 20W50. All right, so that is the most noticeable difference between the two. Now, how the system works, okay, briefly, and I will say brief because I would be sure to put you guys to sleep if I went into any detail, if I haven't done so already. How this works is the engine OEMs and the ILSAC and the folks from the API and the additive companies all get together at meetings and trade shows, and they hem and haw and talk about what they think needs to be done next, and then they start to circulate some proposals for what needs to be added to the next generation of stuff. And they're seeking some sort of consensus. Lots of meetings take place, both meetings designated towards this or meetings at the side of a trade show somewhere. And then people will propose things and make counter proposals back and forth and talk about technical feasibilities. And then they put this to votes. So there's several rounds of balloting to come up with this decision making. And then they decide, we need these, to get it to do this, we need to develop this test. So now we need to develop a whole new test. And so for new test development, you kind of going through the whole same process, right? You go to meetings and you propose stuff and you ballot stuff. And it goes through this long and continuous process to finally settle in on what you really want to do. So that's a very short, very brief description of how that process operates. Okay. Let's see, we're at the part of the show here where we usually take questions from the audience. Let's see if we've had any come in on YouTube chat. It doesn't look like we have anything right now. So I will go on to our next section and talk a little bit about the changes in engine design that have led us to need to change our engine oil. Okay, our engine design changes. Really wrapped around one big concept, if you had to kind of summarize it. And it's this idea of power density, okay? Think of density. Think of power. I mean, when you think of something that's really powerful, yet really dense, what do you think of? Okay, maybe that's what you're thinking of. That's really not what I had in mind. Now, what I had in mind is something more like this. Power density, in terms of engines, is getting more out of less. That's it really in a nutshell. And this particular graphic is pretty clear on that. Take a look at this. We've got a 1991 SUV and a 2014 SUV. Okay? The 1991 SUV has a V6 in it. 6-cylinder engine. Okay, the 2014 one has a 4-cylinder engine. And yet that 4-cylinder engine cranks out almost 100 more horsepower. That's a 65% improvement in horsepower from a smaller engine. All right? That's getting more from less. I mean, take a look at the combined fuel economy on these things too. On the 1991 vehicle was giving you 16 miles per gallon combined, and now you're at 23 on the combined for the 2014 vehicle. That's a 43% improvement in economy. That's pretty remarkable improvement with what these engine makers are doing. Okay? But it does come with having to work hard at designing and building an engine and keeping it robust. So let's go into these in a little more detail here and what we have. The biggest thing, the one that probably is playing a huge role out of all of it, that's newer technology, is gasoline direct injection. Okay, the gasoline, your fuel is directed into the combustion chamber and not into the incoming air. And I'll graphically show you this here in a second. But this idea of direct injection is not in itself new. This is how diesel engines work. Okay? Diesel engines have always had direct injection of diesel fuel into the combustion chamber. And if you've ever worked on these things, you know that a diesel fuels injector is a beast kind of thing compared to a gasoline port fuel injector. Is a much smaller and less complex piece of equipment. So it is a different task to be able to inject into the combustion chamber. Gasoline engines historically started out with carburetors. You have a carbureted air-fuel mixture. They were supplanted for a while by throttle body fuel injection, okay, where the carburetor's taken off, this throttle body unit's in there, and now you're injecting in its place. You're more precisely controlling your air-fuel mixture. And then that got supplanted by port fuel injection, injecting your fuel immediately ahead of your intake valve on the top of the engine. All right, so we've just moved it by going direct injection one step further into the combustion chamber. Okay, the adoption of these things has skyrocketed. I've got a chart on that in a little bit. I will show you. Volkswagen has been pushing this, or has had this technology, and they've been working on it a long time. Everybody else has been more rapidly following suit. The challenge with this particular engine design is this idea of LSPI, low speed pre-ignition. If you've seen any other GF-6 presentations or seen any magazine articles, this LSPI is all over it. Okay, it is the big challenge here, and we'll have more on that as well in a little bit. All right, now here's an animated picture of what this direct injection looks like. So you have this graphic here. We're looking inside of a cylinder, right? You've got the intake manifold coming in there, and the injector is shown here just below it, and that spark plug in the middle. This will take you through all 4 of the 4-stroke cycles. So let's start that up. Okay, so it's going through there. They see what's coming in on the intake is just air, and the injector there blows it in, spark plug lights it off, and you get your power stroke. So we're injecting immediately into the cylinder, not into the not ahead of the intake valve. And this is that chart I mentioned on gasoline direct injection adoption. Okay, take a look at this chart. It's pretty interesting stuff. You can see that band on the bottom, the slowly increasing gray band. That's diesel engines used in passenger vehicles. It's a slow growth, but steady. You can take a look at that blue area. That's your typical either what was carbureted or port fuel injected, the typical way of doing it. And you can see that for a long time that was dominant. And then came the onset of gasoline direct injection. That's the green area. And you look at it, we're right now where that red bar is, right? So you can see it's already made huge strides into the engines out there, and it's predicted to keep going, to keep on going into the future even more. So this technology is, I think, because it's so effective at improving the power density, is here to stay. Okay, the next engine design change worthy of note is advanced turbocharging. Okay? Turbochargers by themselves have been around a really long time, certainly in diesel trucks, very long time. Found their way into passenger cars after a while, not without some hiccups and starts and some other challenges, but advanced turbochargers are reduced lag, and they've worked at resolving lubrication-related issues, so there's, at least in the turbo design itself. So there's a lot of this out there now, a lot more turbocharged engines. Again, another problem with those, low speed pre-ignition, especially when coupled with gasoline direct injection. Okay? That low speed pre-ignition problem comes up again. And turbochargers can also give you challenges with high temperature deposits and varnish. And you can, as you would imagine, they are extremely high temperature things going on in turbochargers. Other engine design changes include variable compression ratios. This is kind of an interesting concept, and I'll have a picture of this in a little bit, but a variable compression ratio engine can be prone to both varnish and sludge. Okay? And here's an animation coming up next here on how this works. This will be, I'll try to talk you through it. It is kind of an interesting concept. Typical of compression ratio has to do with how much you're compressing what's inside your cylinder. And you can change compression ratios by having a different bore or a different stroke. What this mechanism does is it allows you to change the stroke on the fly, right? Your bore is going to be fixed, but your stroke is going to be adjustable. So Infinity has come up with an engine that does that. And it does it by using this little cam lever to adjust another set of levers that adjust the stroke of the engine. And you can change it from, in this case, I think it's 8-to-1 to 14-to-1, depending on whether you want, torque power or whether you want really high efficiency burning. All right? So let's take a look at how this works. All right, you just saw that cam thing move, and it changed from red to green. That's the kind of motion, that's what's going on. Your power stroke, you're in this position, right? You've got your 8-to-1 compression ratio going. Now you shift it over, and you get a longer stroke, and you're in the efficiency mode. back, saw that shift, went back to the power mode. These shifts take place over the period of like a second or something like that when you're on the fly. Okay, here's some more imagery of that. Greater power and torque down to 8-to-1. And now you can see that cam thing has moved, and you're getting a higher compression ratio, something like 14-to-1. Very interesting technology. All right, the next notable engine design change that you may have experienced yourself, start-stop engines. Okay, start-stop engine is one that saves idle. So you come up to an intersection, you put on the brake, your car comes to a stop, your engine shuts off. And the first time you drive one of these in a rental car, you say, "What's going on here?" But you find out that even when you take your foot off the brake to go over to the accelerator, by the time you're at the accelerator, the engine's been started back up for you. This is kind of strange. All right, this is a real common anymore on newer vehicles. But as you might expect, something that has to start and stop a lot is going to be more prone to wear. Okay? It's also going to be more prone to creating sludge inside. So we've got to consider that with our new oil. That's an effect of the design change. And then the final design change thing I wanted to talk about has to do with the need for fuel economy. As it should be pretty obvious by now, the engine OEMs are all but obsessed with engine economy. And we talked about how the viscometrics play an important role with that. Your thin oil gives you contributes to great economy. Well, what happens if your nice thin oil you put in there, as it starts to age after 1,000 miles, suddenly starts to thicken up from aging? What happens to all your fuel economy savings, right? Well, they go away. So important in these new engine designs is the need for fuel economy retention. In other words, that your oil doesn't thicken with use, that it doesn't go out of grade, and that you maintain the kind of economy benefits you had before. All right, let's see if there are some questions that came through the chat here. Hey, we got a question. Is there any correlation between viscosity and protection? What I'm trying to ask, if we weren't worried about fuel economy, are we better with higher viscosity? Or does that depend on engine build? And that is a great question. If you weren't concerned with fuel economy, then it really wouldn't matter. But the fact is that the engine designers are doing a pretty good job at designing engines that aren't sacrificing by having lower viscosity product in there. I mean, ask anybody who's got 300,000 miles on a Honda engine that came out with 0W20. Anybody here around remember when 0W20s first came out? Well, the common response to that was, "I'm not putting that in my engine," right? 300,000 miles on a Honda yawns at 0W20. So I think it has to do with great engine design. And we've not seen or heard reports of anybody who's really complained about having sacrificed engine wear and engine performance in those kind of situations. I mean, you're building yourself a muscle race car, that's a different ballpark. All right. Let's go on to the next section. We wanted to talk about when I saw a number of the GF-6 presentations in the past few months. I've seen them from Chevron and from Phillips 66 and from Citgo, and I think one or two of the additive companies. And every GF-6 presentation I went to, they put up a spider chart. So we're putting this presentation together, and I go to Andre and I say, "Andre, we got to have a spider chart. As you can tell, Andre's a marketing guy, not an engineer. So, I will spare you the spider chart. You don't have to see one. But we will go over each of these features of GF-6, okay, the important features here. All right, so the first, as I've been probably beating into you by now, is to prevent low-speed pre-ignition, prevent LSPI. Okay, LSPI bad. Does engine damage, that's first and foremost. It's also very noisy, okay, creates engine noises, and it results in poor performance, like poor acceleration and stumble, that sort of thing. Okay, so it's a bad thing. What is it? Here's a little more detail on what we know about it, or what the research had shown us about it. The most susceptible are, as I mentioned, a turbocharged gasoline direct injected engine running at 1200, 2700 RPM. That's where the term low speed comes from, as opposed to a pre-ignition that shows up at 4,000 or 5,000 RPM or something like that, okay? It's a very violent knock, leads rapidly to engine damage, and the cause of it is multiple. Well, there are multiple causes. I mean, there are fuel-related factors and there are mechanical-related factors, but there are lubricant-related factors. So the lubricant-related factors, the lubricants are not being asked to address mechanical things, but they do address the lubricant-related problems of things like present deposits, as well as oil droplets that might be present in the combustion chamber. This was originally addressed. This is one of these things that came up in between service classification grades. There was already an SN in place, right? They knew SP was still coming away down there, but they had these engines that were having problems and were getting damaged. What do? They came up with an interim classification called SN+, where they started to address LSPI. Okay, so it's not the first time it's been addressed. Again, it's that important. All right, we've borrowed some video from our friends at Phillips 66 to give you an idea on what normal combustion versus something like LSPI might look like. This was done from a study on a fired cylinder with a glass cover on it, where they could take a photograph of this combustion taking place and then slow it down as they do. So we're going to take a look at some normal combustion and then some abnormal combustion. Okay, remember you're looking down onto the cylinder, spark plug is going to be in the middle, and this flame front is going to propagate from there. So let's take a look first here at normal combustion. Okay, it's going to point out in the middle, that's where the spark plug is at, and the flame is going to initiate from there and give us a nice pressure wave that goes evenly across the piston, drives the piston down, moves the crankshaft, everything works great, right? This is how it was designed. Nice, smooth, even combustion, goes all the way down. Now, when you have LSPI, you end up with ignition that's not in the middle, but maybe starting towards the edge, like that. See that, how it started toward the edge and moved its way across? All right, this is not what the engine was designed for. This is causing the piston to move in ways to the side it wasn't designed for. This is causing an uneven load, or not exactly designed even load, on the connecting rod and the crankshaft, okay? Lots of bad things going on with abnormal combustions. It also can cause a hot spot at the place this is happening and weaken the metal or weld through the metal there. Okay? So you can end up with some pretty serious damage from low-speed pre-ignition. Take a look at these pictures. These are a couple of pistons that were pretty beat up from that. That's the stuff that these OEMs are really concerned about. Okay. All right, so that's the LSPI part of this. Let's talk about some of the other new features involved in our GF-6 SP oil. The next is this reduced cam chain wear. Okay, the prevalence of chains driving around in these engines becoming greater and more important. As all of this stuff is so critically timing controlled, you really can't afford to stretch or wear your chain, right? I mean, if those of you who've been around long enough, at least as long as I remember when I was working on a lot of cars earlier, your timing chain could jump a tooth or two and keep running, right? It's crazy. That couldn't happen now. That couldn't happen now at all. And part of the thing is we've got multiple chains going on an engine. Here's a little video clip from Hyundai showing a number of the chains that are in one of their engines. So we got a chain down to that lower balancer thing. We got that big chain that goes up because it's got dual overhead cams. All right, lots of chain lubrication necessary. So that's important. We also need to reduce sludge. Okay, remember we're getting sludge from start-stop engines. We got some sludge that can show up in these variable compression engines. So that's a feature of GF-6. We're going to reduce sludge, and we're also going to reduce high temperature deposits. Okay, remember we saw those were probably going to come at us from turbocharging, most likely. All right, so sludge, deposits, chain wear, LSPI, and we're going to prevent viscosity increase. All right, we're going to try to retain the fuel economy that our nice low viscosity was giving us. All right, but I told Andre this should be an infomercial because now I've got to say, but wait, there's more. Here's our surprise. You don't get just one today, you get two GF-6s. Yes, folks, there's a GF-6A and a GF-6B. All right, so let's clear that up because that could probably confuse some people as well. GF-6A refers to the usual viscosity grades, the ones we're used to, the 0W20, 5W20, 5W30, all right? And those are all still designated when you go have a container, a quart or a gallon or something like that. The label icon is this API donut with the regular viscosity grade designation in the middle, okay? GF-6B is the new guy on the block, okay? GF-6B is to represent the new lower viscosity grades. In this case, the official one in here in the system as part of GF-6, GF-6B, is 0W16, okay? This is the same category, though, that in the future I would not be at all surprised to see 0W12 and the 0W8. And they did grant this a different label icon, obviously wanting to avoid people confusing it with the normal viscosity stuff. So hopefully you don't go into the store, grab a bottle off a shelf without noticing that, hey, it's got a shield on it and not a donut. And notice how that the 0W16 is even more prominently displayed on there. That hopefully that'll grab people's attention that this is a different viscosity grade than what they're used to getting. Okay. I also decided to talk a little bit about the timeline behind GF-6 API-SP. I already talked a bit about the process, and this is all related to that. Okay. The GF-6 was originally proposed in 2011. What were you doing in 2011 when they first started circulating these memos about what do we need to do to improve the next set of motor oil specifications? Okay. They expected to be done in 2015. Yep, they managed to stretch that work out into 9. We got some people around here that know how to stretch work out that good. They could serve on these committees, I guarantee you. All right. So it's no coincidence, of course, that we have a picture up here of a glacier. So that's about how these things move sometimes. And a lot of the reason it was slow had to do with the testing requirements. Okay, the engine tests run on this. The tests that you run for these service classifications are not beaker to beaker kind of tests. These are fired engine tests. Okay, this is run in actual hardware, and it's not just oh, let's go over to the junkyard and get us a spare engine and run it on. No, you have very carefully made engines, and more importantly, you have carefully calibrated, serialized, and traced parts that you're putting in these engines, that you measure them before and measure them after. Okay, it's a very specialty kind of thing and not easily or inexpensively done. Well, there are 8 tests needed for API-SP. 8 fired engine tests are needed. 7 of them had to be developed from new. I mean, that's a lot of work. I mean, you go over the history of this stuff, and it might be 1 new one per series, or maybe they had to change 2 or 3 tests. 7 of them for this classification. And remember that whole development process that we talked about before. The tests have to be developed, they have to be voted on, they have to be validated and calibrated, and enough people have to run them that when all of the people who make engine oils want to have theirs run, that they can get it run in time to get it to the market in a timely manner. That's one of the reasons, probably the key reason, that this whole thing took 9 years. Okay. And one other thing I'm going to address, because I do get this question a lot, and hopefully I will reduce confusion and not increase it, but that's always a risk that I take when I go out on a limb like this. Where does dexos fit in with GF-6? Okay. Dexos is a specific General Motors specification and trademark for motor oils that they've come about with their own, utilizing much of the same testing that we see for any of the ILSAC series engines and the API stuff. Currently, the current spec is Dexos 1 Generation 2, okay, for passenger car engines. It's very much like the API SN+. Covers a lot of the same ground, does a lot of the same stuff. All right. Now, just because oil meets SN+ does not mean it's Dexos 1 Gen 2 approved. Don't get me wrong there. You got to go through a separate approval ringer with GM and pay their licensing fees if you want to do that. Okay. The current one, now the new GF-6 API-SP, probably would say that it would meet that. I mean, it doesn't technically, you could submit it, but I would guess that anyone who would submit their GF-6 SP product, if they submitted it to GM and paid the licensing fee, that it would probably get covered under Dexos 1 Gen 2. But coming soon will be Dexos 1 Gen 3. Okay, even further improvements in oil from GM, the requirements. It's kind of an SP+, even though SP+ is not a technical term yet. What GM is said to be thinking about in doing this is tightening the oxidation and the deposit limits, the sludge limits. So they're running the same tests, but just a tougher threshold for passing. Okay. In addition, they'll be requiring slightly lower ash content in the new oil and slightly lower volatility of the oil in the engine. All right. So that is my Dexos summary. All right, and it's time for questions. Let's see what came through. All right, we have a couple of questions here. One of them, have there been any long-term engine tests with 0W16 or 0W8 to determine engine life? Some consumers might be leery of extending engine life with lower viscosity grades. The answer to the response to that is I would be leery. I certainly understand that. I don't know of any specific studies, and 0W8 is not in the market now, but I do know, and here's where my thinking is at, the pioneer behind these lower grade stuff, both 0W16 and 0W8, is Honda. And Honda's seems to be pretty obsessed with engine durability and long-term engine durability. So I have no doubt that any testing that's being done is being done by them. And we have another question in here. that says, from a practical perspective, what kind of noticeable performance issues or indicators would we see if LSP was happening within our vehicles? And what you would probably see is certainly under lower load, okay? So again, in that same, that RPM band from 1200 to 2800, somewhere in there. So under acceleration, you're getting engine stumble and the typical knocking and pinging noise. Okay, knocking and pinging noise going on. That would be the, but it's not under really high load. It's not necessarily when you're revving, racing to scream up on the on-ramp to get up to speed with traffic. This would be when you're just accelerating away from a light very carefully and you get that kind of knocking going on in poor engine performance. All right. Very good. Well, I want to thank everybody for joining us today. It's been wonderful having you here. And I've got to say, I didn't see anyone falling asleep. That, of course, is because I can't see anyone. But I want to thank you again for coming today. Look forward to seeing you next time.